It's my pleasure to introduce Varun Bhalerao. So Varun is in our department as an astrophysicist. He obtained his BTech in no department other than our own electrical engineering department in 2006. And in fact, his BTech project was on antenna design with Professor R.K. Shivgaonkar. And since I was also looking at Gymkhana related issues, I know that Varun was always interested in the Kritika Club. I think he was in fact anchoring it. So he was into astrophysics as a very serious hobbyist, even while he was a BTech student here. He went on to do a PhD from Caltech, which he completed in 2012. And during in his as a part of his thesis, he worked on a project called New Star, which was the first focusing of hard X-ray telescope. This was a Caltech JPL NASA mission. And he also studied high mass X-ray binaries with optical and infrared telescopes to measure neutron star masses. So this all goes towards relativistic astrophysics and the latest developments. Subsequently went on to a named postdoctoral fellowship at IUCAA in Pune, named after Vaidya Rai Chaudhary. So he held this Vaidya Rao Chaudhary fellowship for about 3 or 4 years, during which time he was involved with the Indian mission AstroSat and designed the cadmium zinc telluride imager, the so-called CZTI imagers for the multi-wavelength telescope project. He subsequently joined us in 2017, and his work is related to so-called GROWTH, Growth India, which is acronym for global tracking of a particular astrophysical event by all different wavelengths of observation. And he has joined it and made IIT Bombay a part of this international project. His group leads the Indian effort in the study of the electromagnetic counterparts for gravitational wave sources. This is also one of the growth aims. And he is also recipient of Vainu Bappu Gold Medal, which is the highest honor of the Astronomical Society of India. And he's an associate of the Indian Academy of Sciences and recipient of the DST Inspire Fellowship as well. So over to you, Varun.
Thank you very much. Thank you, Professor Yajnik, for the introduction. And I'd also like to start by thanking IIT Bombay for the wonderful opportunities that have been presented here and which have led to these awards. So thank you very much for the awards as well. So what I'm going to talk about today is building astronomical instruments, and I've called it an engineering foray into astrophysics because as was just told, I actually did electrical engineering right here, and then I switched to astrophysics, and that is something which warrants a little bit of explanation. So let me go into that. When we usually think of astrophysics, the idea that comes to mind is telescopes and observing. Astronomy, astrophysics, conventionally, the basic idea, perception is about observing phenomena happening in the universe and then interpreting those. For instance, if you look at this year's Nobel Prize in Physics, then and you see these three wonderful people here, you would think of Roger Penrose as the person who did the theory of black holes, and Andrea Ghez and Reinhard Genzel as the people who actually observed those objects and proved the existence of a supermassive black hole in the center of our very own galaxy. The part which gets forgotten though is how exactly did they do those observations, and why could someone else not do them? And that has to do with the really high quality instruments that were developed in order to make these observations possible. And that is the part which is astrophysical instrumentation. And since I come from an engineering background and I enjoy the engineering aspects of it, that is what I do. So these are the three main missions that I have been involved in so far. One was this satellite called New Star, which was launched in 2012. which is something I worked on during my PhD thesis. And then after returning to India, I've been working on AstroSat, the cadmium zinc telluride imager. AstroSat is India's first multi-wavelength space telescope, and then the Growth India Robotic Telescope. So I'll talk about all of these in the next few slides. So I was told that I should mark out the two parts of my talk for the two different awards. So this is about the Early Research Achiever Award, and this is pertaining to my work on the electromagnetic counterparts of gravitational wave sources. So I'm sure you have all heard about gravitational waves. What is shown here is a simulation of a whole bunch of binary black holes that are orbiting each other, and as they orbit, they slowly come closer and closer because they are emitting gravitational waves. So these gravitational waves carry angular momentum, they carry energy, so the orbit shrinks. And as these objects come closer and closer, they finally merge into one. And advanced gravitational wave detectors detected the first of these back in 2015 and have been detecting many more since. And in fact, you'll soon be hearing a lot more about gravitational waves again. There is even a LIGO India project that has been approved where we will set up one of these detectors in India for the study of such sources. Now, all the animations that are being played on screen right now pertain to black holes merging with each other, and the name black hole itself comes from the fact that these actually don't emit any radiation. You are not going to see anything coming from these sources, but those are not the only type of sources that gravitational wave detectors can detect. In fact, as I'm speaking right now, my mass is moving around, so I am generating gravitational waves, but in an extremely tiny amount. So the waves that are detectable right now largely fall in the class of what are called compact binary mergers. But there is another very interesting kind of compact binaries called neutron star binaries. So neutron stars are these extremely massive objects, 1 to 2 times the mass of the sun, but they are smaller than the city of Mumbai. So the diameter of a neutron star ballpark is about 30 kilometers. So that makes them ultra dense. The density at the core of the neutron star is a factor of 2 to 3 higher than the density in atomic nuclei itself. These are the most extreme environments in the universe by any measure. They are the most compact. They have the highest densities, highest magnetic fields. They are among the most rapid rotators. Some of these neutron stars actually spin around themselves in a few milliseconds. So these are very good natural laboratories where we can conduct the kind of measurements that would be impossible in any terrestrial lab. Now, what I'm going to play next is an artist's rendering of a merger of two neutron stars. And a very important feature about neutron stars matters here, which is that neutron stars actually have a surface, so they can emit light and we can see that light. So let's play this. So you have two neutron stars being shown here. What is being shown as blue waves going out are the gravitational waves. Of course, you would not see them, you would only see the distortion of stars behind them. And the neutron stars, when they merge, there's a massive explosion which actually creates a debris disk in the orbital plane of the neutron star. You end up launching two jets. The jets will then go out at relativistic speeds. They will interact with material which we call the interstellar medium or the circumburst medium in this case. And these particles will then transfer their energy. All of this will get mixed up and you start emitting radiation across the electromagnetic spectrum. So this was an event which was actually detected in August 2017. And in this particular event, we detected electromagnetic radiation across the entire spectrum, going from the lowest frequency radio waves, then submillimeter, millimeter waves, infrared, optical, ultraviolet, soft X-rays, hard X-rays, gamma rays, everything. Now, why does this matter? Why is this so interesting? So, gravitational waves themselves are something that probe the gravity. So, gravitational waves tell you something about the mass distribution of the object. You are going to hear about or learn about masses, orbits, where the source was on the sky, how far away it was, and that's it. On the other hand, electromagnetic radiations, largely speaking, come from the surface or the outer regions of these objects. So that is going to tell you properties about what kind of material was ejected, whether there was any relativistic motion, whether there was any nucleosynthesis that took place there. So in the opening talk today, we heard a lot about lanthanides. So here is a periodic table, astronomers version of a periodic table. And the color coding here shows where the elements were created. So if you look at the hydrogen in the universe, all of it was created in the Big Bang itself, and so was most of the helium. But if you look at oxygen, all the oxygen that we are breathing was actually created inside massive stars, and it was spread around in the universe by the explosion of such massive stars. And the reason why we have any oxygen on Earth at all is that the Earth itself, the solar system, was created out of the ashes of one such dead star. On the other hand, if you look at carbon and nitrogen, again important for life, a large fraction of those was created from dying low mass stars, where sun or lower mass stars will actually have a different kind of end of life phase. Now, I want you to focus on the bottom of this, the lanthanide series, as well as certain elements which are of high value right now, especially in festive season, like gold and silver, and they are all color coded purple. So those are formed in processes what are called R process nucleosynthesis. And these in the universe, we believe that the dominant site of this, possibly the only site of this kind of nucleosynthesis, is the merger of such neutron stars. So there are various other science aspects as well. I will not go into full details of all of them, but broadly speaking, the idea is that we want to study equation of state, we want to study jet physics, we want to understand how magnetic fields work, and how magnetic fields, what happens to these fields when these neutron stars combine into a black hole, where is the nucleosynthesis taking place. And to do all of these, we want to study these electromagnetic counterparts to these gravitational wave sources. And we have a large group here, of course, but also spread across various Indian institutes and around the world. We work together to address some of these problems. So, how do we go after these cosmic explosions? Well, the first tool that I'm going to talk about is something called the cadmium zinc telluride imager on AstroSat. So, on the left, you see an image of AstroSat with a few people working under it. This is about a 2-meter cube satellite, state of the art observatory. It was launched in 2015. So, in fact, we have just finished 5 years of AstroSat in September. AstroSat has 5 different telescopes that cover a multi-wavelength range, so that if you are looking at any object, you will study it in optical, ultraviolet, soft X-rays, and hard X-rays. But what I want to talk about in particular is this instrument which you see here, and you can see me standing next to it. This is a laboratory qualifying model of the same instrument. This one is called the cadmium zinc telluride imager. So CZTI is what we call a coded aperture mask instrument. It works in hard X-ray regime about 20 to 200 keV. Colloquially, when we say X-rays, if we are looking at, say, airport baggage scanners or medical X-rays in the hospital, these are typically 40 to 60 keV kind of range. So it's the same range that we are looking at. And what is really interesting about CZTI is that although it is pointed in a particular direction, which is upwards, as seen in this in these images here, at high energies, CZTI is actually sensitive to photons coming from all over the sky, and we can use that very nicely to study such explosive events in the universe. So the detectors that we use are actually medical detectors. We buy them off shelf from a certain vendor. But these detectors are actually very interesting devices. When we usually think of imaging, for example, if we are talking about taking images with a normal camera, you have a shutter and you open the shutter, you collect light for a certain amount of time and you close it. But you can't do that with X-rays, where, for example, the very high school introduction of X-rays itself says that it is radiation that goes through everything. Going back to this slide, we have actually detected cases when X-rays came all the way through the entire satellite and were incident on our detectors here, and we saw them. So how do these detectors work? These are 5 millimeter thick cadmium telluride detectors, cadmium zinc telluride detectors, and they record the position, the time of arrival, and the energy of every single photon that was incident on. And thanks to very nice work done by ISRO and all the institutes working to build AstroSat, we actually have the right kind of onboard capabilities to process this data and the bandwidth required to download all of it. So we measure continuously how the intensity of any source in the sky was wherever astrosat is pointed. And when we do that, we sometimes see things like this. So there are a lot of graphs here. Let me start with this one, which is rather large and easy to see. What you see on the x-axis is time in seconds, and we have picked 0 at the peak of this. So this is spanning about 1400 seconds of time here. And you can, what is plotted on the y-axis is the intensity. How many X-ray photons are we receiving every second? And you can see that there is a random Poisson fluctuation going on here, but suddenly you see these large spikes, and sometimes you see one, two, sometimes multiple, and we have seen them at all sorts of time scales. So on the left panel, for example, the time axis is spanning only 20 seconds instead of 1500, and you can see that we have detected a lot of these bursts. So astrosat to date has detected about 330 of them, plus another 70 that our group working right here. And I noticed that several of the students are who work on this are actually in the audience right now. So these are the kind of explosions that we are looking at. And the moment we see such a burst, what we do is we start analyzing that. We try to understand what the properties of the gamma ray burst were. Now, with sensitivity like this, we are actually, in terms of number of gamma ray bursts discovered, we are on par with an instrument called Swift BAT. So if you globally ask what are the satellites that study gamma ray bursts, then there's a NASA mission called Swift, the Neil Gehrels Swift Observatory, and there's a joint NASA ESA mission called Fermi. And these are the two missions which were specifically designed to study gamma ray bursts. And what is really amazing is that CZTI, which is a small instrument which was designed to do a certain task, we have repurposed it very, very nicely to study GRBs. And we detect as many GRBs per year as Swift BAT does, which was a specialized mission designed for just this. With this kind of sensitivity, we should have seen that neutron star animation that I just showed you about when that was detected in many wavelengths. Astrosat should also have detected it, but we did not. At that time, we first were really disappointed and confused as to what happened, but we were also very confident about our instrument and the abilities of that instrument. So we took the known properties of this burst, which was detected by a couple of other satellites, and we said, should we have seen it? And yes, we should have had a very, very high SNR detection of that source. So what that meant is that there is only one way that could have happened. The source must have actually been hidden behind Earth. And so what is shown here is a series of images. So let me explain a few. This is a projection of the entire sky. And this brown region that you see here, which is marked GBM, is the localization region by the Fermi satellite, which detected this burst. And it said it is somewhere in this part of the sky. The burst was not very bright, so they could not pinpoint the location. And this white circle that you see here, this is the area of the sky that was hidden behind the Earth as seen by Astrosat at that instant. So we said that based on our non-detection, actually, the burst cannot be in this half, and we could actually reduce the Fermi localization area to half, which helped in concentrating other resources. These kind of results help on that front. And then finally, this was the error region that was computed by LIGO and so on. And somewhere here, with the position marked by these pink marks, this was the source which was detected. So this is a very zoomed in picture. On the scale of this all sky map, it is smaller than the laser pointer dot that you are seeing on the screen. So even non-detections with our instruments are very, very meaningful statements about the properties of the object.
Varun,
So
again,
yeah,
uh, you probably need to wind up in about 2 minutes or so. It's,
sorry, I was told that I have to give the two talks in order. So this is my last slide from the first one. Do you want me to stop after this one?
no, you can maybe accelerate for the next part. We are almost
Okay,
towards 12, so yeah.
okay, okay. So, so yes, we have gotten some really good results out of it. A lot of undergraduate students working on it. They have also participated in writing papers. In fact, Aero BTech student led one of the papers. You might say, okay, what about the others? Well, we are submitting 4 papers this weekend, and a lot of undergraduate students and postdocs and PDFs and everyone have been involved in this work. And that's really all 4 papers being submitted on this Saturday. The second part, which I was going to talk about, is the Kriti Ramamritam Award for Creative Research. And this is something which I'm now going to skip through and go a little bit fast on. So what you are seeing here is the dome of the Growth India telescope located at this amazing site in Ladakh on Mount Saraswati. You can see the Milky Way rising behind it in this time lapse. So Growth India is this robotic telescope. The primary mirror is about this size, 70 centimeter aperture. We have a very high quality camera that is coupled with it. A few pictures from the site and first light. I'll skip that. So the purpose of this growth project, growth stands for global relay of observatories watching transients happen. That's quite a mouthful. It is an international collaboration. I am co-PI of the Indian part. We have been the three key goals of this collaboration are to study these electromagnetic counterparts of gravitational wave sources, to study asteroids, and to study young supernovae. So a little bit of aside, we have actually been doing some really cool work with discovering and confirming objects of asteroids. You may have seen this press release a couple of months ago, which was covered in a lot of media outlets, also drew attention of the government, where our students working on this project actually discovered the closest asteroid that flew past Earth without impacting the Earth. Uh, Here's another one. This is an asteroid which was discovered by our students and confirmed by our students. So you can see the asteroid whizzing past all the stars there. Asteroid is marked in the center. And we have actually three students who are working on this. Two undergrads and a grad student have discovered more than 40 asteroids and comets and confirmed orbits of several. So I made these slides yesterday. This is already outdated because last night one of the students told me that three more of our comet confirmation observations have been accepted by the International Astronomical Union. Um, but it is not just about pretty pictures. This is the part where really the focus of the award was. This is a diagram made by Harsh Kumar, the PhD student working on it, and this is all the back end of this telescope. So if you look at the research class telescopes in India, Growth India is among the smallest of those. But if you look at it in terms of publications, we are actually number two. And the way we can do that is that we heavily focused on standardizing and automating the telescope. So I don't want to walk you through the flowchart, but what we do is that we have a fully autonomous system where anytime there's a transient explosive source or anything of interest discovered anywhere in the world, it is relayed onto a machine-to-machine network with a machine-readable protocol, XML-based protocol. We actually look for those alerts. The telescope sleuth there starts taking observations. The data are automatically downloaded to IIT Bombay. They are fully processed. And at the end of the day, end of the night rather, when we wake up in the morning, we get a table of numbers saying that at this point, this was the brightness of the source. So what this does and what it has enabled us to do is that it shifts our focus from the effort of acquiring the data to the creative task of interpreting that data. And by focusing on this aspect, we have been able to, you might want to call it, industrialize our observation process. And as a result, since 2017, we have, from this collaboration, we have 15 refereed papers, including two in science, one in nature. There are a lot of students and interns working on it. We have what we call circulars and telegrams. And if you count these circulars, telegrams, and MPEGs, which are non-refereed publications, which are quite important in astrophysics, then we have crossed the milestone of more than 100 publications from this. And we have two more in prep, which will be submitted in the next month or so. So all of this, of course, would not have been possible without having a great team to work with. So we call ourselves the Space Technology and Astrophysics Research Lab, or STAR Lab in short. And here's the awesome team of my colleagues, students, postdocs, and undergrads. And all of them work very, very hard on to make all of this possible. And of course, none of this would have been possible without the support and the environment at IIT Bombay, where there's a lot of encouragement. I've found some great mentors here who are helping me through with all of this. So thank you very much for all of these resources. To conclude, I will point to what's next. So we have proposed this highly ambitious mission called Daksha to ISRO. Daksha will consist of two satellites orbiting on opposite sides of the Earth, and these will actually be about an order of magnitude more sensitive than the Fermi and Swift satellites that I've been talking about, in order to detect these kind of cosmic explosions. So this is a team comprising of several people from 4 departments in IIT Bombay: aerospace, electrical engineering, mechanical engineering, and of course physics. Plus we have external collaborators from various institutes around the country. So this is the project we are working on now, and I'll say stay tuned. It's a magical universe out there awaiting to be discovered. But instead of saying stay tuned, I will say come on and join us on the ride. Thank you very much.